Okay. Last time we were doing an experiment of tossing a coin for 10 times, right? Anybody still remember the final results? We got head 6 times and tail 4 times, right? Tail 4 times. Okay. So here, this is the equation to calculate the entropy for a possible situation. This is actually the statistical definition for entropy. Thermodynamics formula for that. So entropy equals to the Boltzmann constant times the log of the possible microstate for the desired situation. Okay, so let's do an example to see how we can utilize this equation to do it. So for example, here, suppose you toss 100 coins starting with 60 heads and 40 tails. So your initial state is going to be, let me do this, head, tail, 60, 40. And then you get the most likely result 50-50. That's the final state. Final state of 50, also here 50. What is the change in entropy? Well, to find this change in entropy, so delta entropy equal to entropy final minus entropy initial. So K ln omega final minus this omega initial, right? But the question is, how are we going to find the amount of possible microstates when they are 60 heads up and 40 tails up versus 50 heads up and 50 tails up, right? So for this coins, these 100 coins, should you use combination or should you use permutation? Why combination? The order doesn't matter here because 100 coins are identical, right? If they're identical, then the order doesn't matter in this case, which we need to use combination. So the first initial state, how many possible combinations are out there? C， 你们是怎么写的？你们是把 100写在这儿还是写在这儿？
是左边。
写左边是吧？然后 60写上面还是下面？
下面。
所以你们是这样写的是吧？
还有一种写法就是，
你们是相当于这种 C60 对吧？我以前体制内学的时候，我记得我是这样子。
这样也可以。
也可以。
你们也学了这个是吧 ？OK， 那我们就用你们习惯的方法吧，那就用这个。Then this one here is going to be 100C50. Do you need to do another times 100C40 here? No need, because if 60 up, then the rest of them must be down, right? So once this is fixed, the other 40 has automatically, because this is essentially the same as this. Those two are essentially the same, right? So that's the amount of possible state. Okay, but we probably don't want to calculate this by hand because it's just going to be too much. So did Mr. Ife teach you how to calculate this using your calculator? Yeah?
Yes.
Okay, so can anybody tell me what is this is how much? 1.37 times 10 to the power of 28. Okay, what about this one?
1.01 times 10 to the 29.
Okay, so 1.37 times 10 to the power of 28, that's the initial state, right? So that's the initial possible outcomes, which is here, 1.4, you only save 2 significant figures times 10 to the power of 28. And then 1.01 times 10 to the power of 29, that is the final So which goes to here, it also only saved two significant figures. So 1.0 times 10 to the power of 29, right? And then you just need to plug in the numbers. KB is 1 times 3a, 1.38 times 10 to the power of negative 23, and then you log it so that you got this final entropy. Okay, so that's how you can calculate entropy here in this case. For entropy, because it's involved in thermodynamics, and in thermal, we always use, most likely, or always study ideal gas, right? We have amount of gases, and anybody still remember the assumption for ideal gas? That they are all identical, elastic, perfect sphere, right? So in this case, if our gas molecules are identical, so identical means order doesn't matter. So whenever we're dealing with ideal gas, if you're not sure whether you use permutation or combination, always go for combination, because our study objects are identical, and thus the order doesn't matter. Okay, so most likely it will involve just combination rather than permutation. Okay, that's this, and let's move on. So, also, I don't think it's possible to answer that because I haven't met any of the possible questions like that. But if, let's say, you are tested to calculate the entropy for a gas system. Now, for 1 mole, how many particles are out there?
6.2.
N equals to 6.02 times 10 to the power of 23, right? See, this has already a law, right? So if you're gonna use, let's say this, if you're gonna use like C, let's say N this, N, and then something here, let's say R, then you're gonna end up getting like N to the factorial, and then R factorial, N minus R factorial, right? This is gonna be a huge number. You either use your calculator or actually try this. Try if you can find the factorial of this number. Your calculator will show. I don't know. I never tried this before. 能够 Math error. So it's too big, right? Overflow. It's too big. So in this case. 那我觉得大概应该是不会考，可能是竞赛里面会出现。竞赛里面我们这个课上就不讲。OK， 那就不用管，因为我确实在 IB 的题里面没有看到过这种类型的。So, for example, let's consider the gas molecules in a room, right? So we have this kind of state. This here is the most probable state, right? But what about this one here?
Almost impossible.
Almost impossible. Let's assume that we only have 1 mole of molecule here, which is definitely more than that. So in order for the other half to be completely empty, this is basically only one possible microstate, right? Out of I don't know how much, maybe infinity, right? So this is almost possible. The probability is 1 over a infinity, which just gives you a 0, right? This may be, but most likely it's still gonna be this, right? So how do we understand this sentence here? Consider the molecules of the gas in the room. In fact, entropy can tell us about the direction of the time. If we're gonna talk about the direction of the time, so which one should be the first and which one should be the final result? If there's gonna be a sequence,
Middle.
which one should be number 1?
Middle.
This should be number 1. And as it changes, it's gonna go this, and finally it's gonna mixed completely, right? Okay. Does this make sense? Okay. Alright, so let's do this here. A liquid is more disordered than a solid at the same temperature. Why is that?
More free.
Okay, it's more free and it can move with more freedom, right? So it's not like a solid molecule who's being fixed at its position, right? And 1 mole of gas in large volume is more disordered than 1 mole of the same gas at the same temperature in a smaller volume. Why is that? If your volume doubled, does it make sense to you that if the volume doubles, the position, the probability for the position of the particle, of the gas particle, also will increase? So, for example, right now, let's say if this is the only possible volume, right? And then you double the volume. Now the particle is not just likely to be here, it can also likely to be here. And then if you double again, then it can be here, 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 right? So there's more probability, so more disorder. More probability than more likely outcome, right? More disorder. So in this case, smaller volume is gonna be more ordered. Like, for example, right now you have this much space. Now you decrease the volume, it can only move between this. And now you decrease again, it can only between here. And again, and then until you fix it here, it can only move here, which is almost fixed, right? So more space you give it to them, more disorder they're gonna be. More structure, less space you give them, then it's more likely that you're gonna find them there, right? Okay. So does that make sense? Can anybody give me an example, like daily example, to show me how you understand this thing, the volume thing here? Let's say if I ask you to 自由活动, how do you say that in English?
It's just free time.
Okay, it's your free time, but you're only allowed to walk around here in C306. It's still easy for me, like everything is still kind of like in order, I can still directly spot everyone. But if I say, okay, it's free time, but you're allowed to walk around the whole JCID, then in order to find each single of you, I need to spend more time to look for you because you guys are more disordered. You might end up being in a math classroom, or you might end up being out there in the field, in the gym, in the bathroom, just could be everywhere, right? So you get the idea, okay? All right, and 1 mole of gas in a given volume at high temperature is more disordered than 1 mole of the same volume but at a lower temperature. Well, higher the temperature, more kinetic energy. More kinetic energy vibrates more, right? Vibrates more, well, it's more disordered, right? Does that make sense? Okay. Okay, so here, let's keep looking. When heat is given to a system, Q is positive, and its entropy will increase. When heat is removed, heat is removed, Q is negative, and its entropy will decrease. For a reversible process that returns the system to its original state, entropy does not change, because entropy is a state variable, okay? Entropy and also internal energy, both of them are state variable, which means it only depends on the initial and final state. It doesn't matter how, during the process, how you change. State variable means it only depends on the states, initial and final state. It doesn't matter how you change from the initial to the final. Okay. So here we give you another definition of entropy, another way to calculate the system of entropy, which is related to the heat energy and its current temperature. So entropy equals to, or changing entropy equals to the change in the heat energy in a system divided by its current temperature. Okay, so let's move on. See an example here. So example, find the increase in entropy of 1 kilogram of ice originating at 0 degree that is melted to form water, also at 0 degree. Can you divide by 0 here?
No.
What should you do?
Choose 70.
Convert it into Kelvin. Right? Convert it into Kelvin. Okay. And what is the heat involved here? For an ice to melt, you need to absorb heat, right? And so the heat here is actually calculated by its latent heat. Delta Q is greater than 0 or smaller than 0 for this case. Greater than 0, so entropy should increase. Changing entropy should also be greater than 0. Alright, so you get this. And then changing entropy would equal to changing Q divided by temperature. Changing Q will be 3.34 times 10 to the power of 5 joule. And temperature at 0 Celsius degree is 273 Kelvin. So your final changing entropy will be this value.
1,001.
Okay. Let's check answer. 1.22 times 10 to the power of 3, so 1,220 joules per Kelvin. Joules per Kelvin. So far so good? Okay. Cool. Alright. Now, let's think about another situation. Let's say, if we apply the expression of delta S equal to delta Q over T, right? Now, think about this case. The flow of heat between a hot object at temperature of T high or T hot to a cold object at temperature of T cold. Now, the heat is transferring away from the hot part to the cold part, right? So for the hot object, delta Q is smaller than 0. For cold object, delta Q is greater than 0. Okay, now if a quantity of heat Q flows from hot to cold, the total entropy change of the system and its surrounding is calculated by this. Change in entropy equal to each of them's changing entropy plus together. That's the total change for this system. Does that make sense? For both of them, the changing energy is going to be the same magnitude. But for the hot object, it's losing heat, so there is a negative sign. For the cold object, it's getting heat, so there is no negative sign. Okay? Which means for the hot object, its entropy is decreasing. Zero. For the hot object, the entropy is decreasing because it makes sense because its temperature is going to decrease, right? It's going to losing heat. For the cold object, since it's getting heat, its temperature will rise, right? So its entropy will increase. But overall, the total entropy will
0.
stay the same. Increase. Why? Because total entropy of the system should always increase. And also, we can prove that. Isn't Q and Q the same? What happened with TH and T cold? TH and T cold the same? If TH equal to T cold, will there be heat transfer between them? Heat transfer is driven by the temperature difference, right? Heat is always flows from the hotter object to the colder object under the natural or spontaneously, right? Without if there is no AC or human intervention. Now we know that TH is greater than TC. So let's say Q is 100. TH is 50. T cold is 20, right? Just for the sake of simplicity. So 100, negative 100 divided by 50 plus 100 divided by 20. This is the decreasing of the entropy in the hot system, which you're going to get negative 2. This is the increase in entropy in the cold system, which you're going to get positive 5. So in total, the entropy still increase. Because here you have a higher temperature, the changing entropy will be smaller. Does that make sense? Okay. So here, because T high or T hot is greater than T cold, that overall the entropy change of system hot and system cold would also increase. Okay, so let's move on. All right, let's look at this example. Spontaneous heat transfer from hot to cold is an irreversible process. Spontaneous, unless you do human intervention, it does work to the system. Calculate the total change in entropy if 4,000 joules of heat transfer occurs from the hot reservoir to a cold reservoir, assuming that there's no temperature change in either reservoir. All right, I'm going to give you 4 minutes. Mingy, finished? Darren, finish. Okay, Darren, tell me the first one.
9.33 joules per second.
9.23. 9.33.
OK，还没减。
Oh,
还有加一个
9.33. Okay. So the hot one, the change is negative 6.67. The cold one, the change is 16. Alright, 16. Okay. So there is an increase in entropy for the system of two heat reservoir undergoing this irreversible heat transfer. Okay. When is the transfer? When is the process reversible?
No change.
When there's no change in entropy, right? That's the only way for the process to be reversible. If there's change in entropy, which most likely is going to be positive, then that indicates the direction, right? The heat transfer is always going to be spontaneously from the higher temperature to the lower temperature, okay? So we'll see that this means that there is a loss of ability to do work with this transferred energy. Entropy has increased and energy has become unavailable, more unavailable to do work. If you have already watched the video that I asked you to watch by Veritasian about the entropy, you know that we're actually getting the low entropy, which is more useful energy from the sun. And then we're giving back the universe the same amount of energy that we received from the sun, but just a higher entropy, which is less useful, right? Because in order to keep our Earth under a constant temperature, the net heat should stays around the same, right? Or the heat change should be 0. Okay. It's just that we're getting more useful energy from the sun, and we're radiating back to the universe with the less useful, less concentrated, or more dispersed energy. Okay, so that's this one here. All right. So this is basically the essence of the second law of thermodynamics, that the entropy of an isolated system never decreases. Okay, pay attention, it's isolated system, not closed system, which means not even energy changes, okay? Not even there is energy for an open system. Is it possible for entropy to decrease for an open system? Yes. Because you might getting more lower entropy energy from other sources, and in that case, it could be possible for an open system. But for isolated system, the entropy never decreases. The entropy never decreases. Also here, the second sentence is also useful. Entropy increase in real or irreversible processes, and it stays the same in theoretical or idealized reversible process, but it never decreases. Okay. All right. There are other ways of restating the second law of thermodynamics. Jason, would you please read both of them for me?
It is impossible for thermal energy to flow from a cold to a hot object without performing work. It is impossible in a cyclical process to completely convert heat into mechanical work.
Okay, so the first one basically is saying that thermal energy is always flowing from a hotter object to a colder object, right? Unless you perform work, unless you use a heat engine, use a AC, use a refrigerator, right? The second one is that it is impossible in a cyclical process to completely convert heat into mechanical work. Like even the most idealized heat engine, the Carnot engine, cannot reach a efficiency of 100%, which we're gonna talk about very soon. For the second form. Okay, so let's look at the heat engine here. What is a heat engine? Heat engine is a device that converts thermal energy into useful mechanical work, right? So basically, it converts thermal energy into mechanical work. Now it needs to work in cycle. As I have already showed you a video last week of how a combustion engine works. That's a similar one. So let's look at this heat engine. What we have is a hot reservoir here and a cold reservoir. It's idealized the system or idealized the engine because we assume that the reservoir has a constant temperature. Okay, its temperature is going to be constant, stay at TH, and cold reservoir, the temperature is going to be constant, stay at TC. Now, we know that heat energy is always traveling from high temperature to low temperature, right? And so for this energy flow, the hot reservoir is given out QH, this amount of heat energy transferring away. And the cold reservoir receives QC, this amount of energy. Can QC equal to QH?
No.
Part of the QH here, if you're going to use it to do work, can output as a useful work. Can Q out equal to QH? No. Q out is always going to be smaller. There's no way to be equal. Always smaller than QH. But if you don't do work, let's say you don't do work, right? Then it is possible for all the heat energy just received by the cold reservoir. That's also possible. But for the work output, it's never going to be 100% from the QH. There's always going to be energy flowing out to the cold reservoir. And in this case, it's idealized because we are not even considering the heat loss to the surroundings, right? Because we know that nothing is perfectly isolated or insulated. There's always going to be heat loss to the surroundings as well. Okay, so for an engine that perform work like this, we're not considering any other realistic condition. For example, there's no heat loss to the surrounding, and the hot reservoir, cold reservoir stay at the constant temperature. The engine perform this cycle is what we call the Carnot engine. Okay, for this engine, okay, we have this Carnot, which is a French engineer, investigate how to convert heat into useful mechanical work in most efficient way. And the Carnot engine is the idealized, most efficient heat engine. Now, we know that we cannot have a 100% efficient engine, but how efficient can we be? That depends on the temperature difference of your hot reservoir and cold reservoir. Okay? So here is the Carnot cycle. The Carnot cycle is super idealized because, first of all, let's look at this cycle. From 1 to 2, this is a what process? Isothermal process, because it stays at this isothermal. From 2 to 3, it is a adiabatic. From 3 to 4, isothermal, and from 4 to 1, adiabatic. Okay, what do we say about isothermal process? In order to perform that, in order to make sure that the temperature stays constant, doesn't change, we need to make sure that heat transfer is sufficient enough to keep temperature the same. Which means that, are we going to do it very quickly or very slowly? Very slowly for isothermal. And on the other hand, for adiabatic, we wanted to make sure there's no heat transfer away, right? There's no heat exchange between the system and the surrounding. And in order to make sure that happens, we need to make sure that the adiabatic process is going to happen
Very fast.
as fast as possible so that the heat has no time to transfer away, right? So those two processes are kind of intuitively against each other. One needs to happen super slow, while the other needs to happen super fast. So, right, so let's dive into the details of each processes. We know that from 1 to 2, it's going to be isothermal compression. Temperature stays the same, but volume decreases. In this case, since it's isothermal, what do we know from isothermal? That temperature doesn't change, so that delta U doesn't change. If delta U doesn't change, according to the first law of thermodynamics, delta C equal to delta U plus W, this is 0 goes away. So all the work that you observe will become the work done, right? Now, since it's compression, the work done will be negative. So the heat is negative as well. Alright. Now, from 2 to 3, it's adiabatic, right? Adiabatic means Q is 0, which means changing internal energy would equal to negative work done. Changing internal energy will equal to negative work done, where work done equal to negative changing internal energy. From 3 to 4 is isothermal expansion, which means work done is going to be be greater than 0, and so is the heat energy, which means the system is absorbing heat, inputting heat. The QH is being inputting into the cycle, and QC is being outputting from the cycle.
Mr. Klein,
Yes?
do we start from 1 or do we start from like 3? What's the order of?
When we analyze, we start from 1, okay? And usually for the question, it would also ask you to start from a certain point. But if it doesn't matter, if it doesn't tell you, you just need to follow the direction. If you start from 3, it's also okay. Then you just need to know, after 3, it's going to be 3 to 4, because the arrow has already been given, okay? And now from 4 to 1, it's another adiabatic, and it's expansion because the volume is increasing. Volume is increasing. Okay. Now, is there any net work done by this cycle, which is the area of the enclosed graph? Okay, and is it the work done, the net work done, is it positive or negative? How do you know it's positive? Well, it's clockwise, first of all. And second of all, even if you don't know if it's clockwise, how to look clockwise, anti-clockwise? We know that when air is being compressed, that work done is negative, right? So this part is air being compressed. When air is expanding, this part is positive, right? So you have more positive work done, right? You end up with this all are positive, okay? That's another way to judge it. All right. So that's the reason why here we have W net equal to QH minus QC. 5 minutes break. And then we're going to continue. Pause the video. Sorry. All right. Let's keep going. Okay. Now, so for heat engine efficiency, let's recall from the definition that we know from MYP that efficiency is calculated as useful work output divided by total input, right? So in this case, the useful output work is the net work done by the cycle, right? Because you're doing work outward, you're outputting work. And the total work input in it, the total energy input in it is the amount of energy released by the hot reservoir, which is this. And we know that the useful work done is the amount of energy provided by the hot reservoir minus the amount of energy absorbed by the cold reservoir. The left is what we use to do work. And then with all the term we divide by QH. We're gonna end up giving ENTA efficiency equals to 1 minus QC over QH. Okay, so this shouldn't be too difficult. You finish noting? Okay, let's move on. So, heat engine, the second law, we need to look at each processes and calculate the change in entropy. Now, for process 1 to 2, actually, instead of directly showing you, let's look at this here, and then try to calculate. Changing entropy from 1 to 2 equals to changing Q over T, right? What is the changing Q from 1 to 2? What's the changing Q from 1 to 2? From 1 to 2, it's a what process? Isothermal compression, right? And so the change in Q, which is delta Q, is equal to the work done in this case by this process, which is this area. And then you just need to divide by Tc if you know the value of Tc. Right. Okay. So here, negative Qc. Why is it negative? Okay. Alright. Delta 23, S23, from process 2 to 3, that's a adiabatic, which means there's no heat transfer, there's no delta Q. Delta Q is 0, so that delta S is also 0. And for delta S34, where we have isothermal compression expansion from 3 to 4, right? So we have QH, the amount of heat absorbed, released, divided by TH at this temperature. And lastly, from 4 to 1, it's adiabatic expansion. Again, there is no transfer of heat energy, so no change in entropy. No change in entropy. Questions? Okay, now for this Carnot cycle, there are many factors that indicating that this is the idealized situation. In real life, we probably cannot get these. Okay, what are those possible indications that showing it's an idealized situation?
That equals slow enough.
Either process slow enough for the isothermal and adiabatic, which is also hard to achieve in real life, and reversible. For a heat engine, well, in this case, because we still have the work done here. This is not a reversible process. It is still irreversible. But we assume that the hot reservoir and cold reservoir has a constant temperature, which you probably cannot find in real life. And we assume that there's no heat loss to the surrounding, but in reality, there's gonna be heat loss to the surrounding. Okay. Right. Oh, that basically just means entropy doesn't change, right? Because, yeah.
Maybe possible.
I think it's kind of like a made-up word, like iso plus entropy. Isentropic. I don't know if it's a real word or made-up word, but this is basically just adiabatic because adiabatic, yeah, doesn't change. It's all right. So we get this: the total change in entropy of the system equals to the sum of those two. You need to look at the change in entropy of the hot system and the change in entropy of the cold system. If the total change of the hot system and the cold system is 0, you end up getting this. And we also know that if the Q is actually this, you need to get this, QC over QH equals to TC over TH. So for a Carnot cycle, this is the efficiency for Carnot engine. Efficiency for Carnot engine. Oh, yeah. So if the total entropy stays the same, then it is irreversible. It is irreversible. It is reversible, sorry. Total entropy stays the same, reversible. Right, because Carnot engine is a very idealized, and even though there is a temperature change, but you really don't know the direction. If it's dumping heat to the cold or the other way. Right, so it is reversible. It is reversible. Okay. So this is the final equation for Carnot cycle. This is only applicable to Carnot engine. If it's not, you still need to use 1 minus QC over QH, not this one. Okay? This equation is only for Carnot engine. Or if you're being asking the maximum possible efficiency for heat engine, you use this one. Okay? For real engine, you cannot use this one. You can only use n-tap equal to 1 minus QC over QH. So there is a condition for which to apply. All right, so for the viability of this heat engine, let's look at it. We have 100 joules, 30 joules that's being absorbed by the cold reservoir, 70 joules output into work done. So first of all, it does obey first law, which energy is conserved, right? 100 joules, 70 plus 30 equals to 100. It does obey the second law. Heat is flowing out from the hot reservoir to the cold reservoir. So we get this equation. This C stands for Carnot. So it's the efficiency for Carnot engine. 可行性。 Okay. So now here, let's think about the practicality of isothermal processes. As we mentioned, in order for a process to be isothermal, for temperature to stay the same, you need to make sure that this thing have enough time for the reservoir to provide heat so that it stays at the same temperature. That means the process needs to happen at a super slow speed, right? So here, let's look at this question. Can you explain at a macroscopic level why temperature increase when you compress adiabatically? Why? Okay, and
when
the volume.
because P1 B1 to the power of 2 over V equals P2 V2 to the power of 2 over V. If your volume decreases, then your temperature will increase. Yes.
T1 V1 to the
Yeah,
power of
12.
2 over 3 equals to
T
constant. So when volume decrease, decrease, temperature has
Okay, so let's see. We have this, which is the first law of thermodynamics, Q equal to delta U plus W. And delta U equal to 1.5 and 2 over 3, which is how we calculate the internal energy for ideal gases. Now, what about microscopic level? Microscopic level, we're looking at the particles. So, if we're looking at the particles, when you compress adiabatically, which means, first of all, you compress, volume decrease, right? Volume decreases, less space for the particle to move around. And adiabatic means there is no heat exchange between the system and the surrounding. You're compressing, which means there's work done on the gas system. The work done on the gas system cannot be transferred as heat away to the surrounding, which means, according to the first law, those work done can only be absorbed by the gas in the form of internal energy. And thus, internal energy increase will cause you temperature increase as well, because internal energy, look at here, is directly related to temperature measured in Kelvin. Okay? 懂了？
不能也这个 microscopic 不能用上面数。
啊，对，不能用上面数。那你也可以用什么？你可以看你的单个 particle 用 EK。Average kinetic energy equal to also 1.5, right? 3 over 2 kVt， 对吧？那你就用 statistic 的那个公式啊，你不用整体的，你不用宏观的公式，你用微观的，对吧 ？OK。power cycle 这个不用管了，这个它考的不多。后面的都是一些 real engines, which also won't test it. This one here, the auto cycle, might test you because it's also kind of special. Instead of doing isothermal or whatever, here it uses isovolumetric, 2 isovolumetric, and 2 adiabatic. Okay. This is a more real example for the Otto cycle. They still cannot be perfectly solved.这些都不会考的太那个啥啊！你看考试的时候就这么方方的，非常的简单。
太好了。
OK， 那我们来看一下这道题，给大家5分钟的时间做一做。别怕，我把窗户打开让可以。
开了。关灯。
哎呀，我的圣诞树。
He's the main actor.
I'm taking only like
我听说在德国你不能打蜜蜂的，你要是打蜜蜂了被人举报，警察会来抓你。
Get out！
做了吧？ 那你们做完再找我吧。
但是我会